Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we're going to talk about the concept of angular kinematics. So that means kinematics with circles. That's all it all comes down to, kinematics in circles. And so remember, we've talked about the W is the angular speed, which is measured in radians per second, right? And we've learned that the angular acceleration, which is going to be the W over seconds, it's actually technically the change in each, or the delta. But it turns out that when we're calculating these, there's also kinematics equations. And if you remember back from our unit on kinematics, we had some equations. You might remember there were three key kinematics equations. If you recall, we can say x2 equals x1 plus v1t, v1x, plus 1/2 at squared. We had v2 equals v1 plus at, and we had v2 squared equals v1 squared plus 2a delta x. These were the main three kinematics equations, which we like to call x1, x2, et cetera, et cetera. Well, guess what? When we talk about angular kinematics, the same equations apply, but we change things around. Guess what they are? They're going to be sigma. So sigma measures how many radians a circle has moved, right? And you can say sigma 2 equals sigma 1 plus W initial, I'll say 1 times t, plus 1/2, and this is the acceleration, right? Acceleration is that Greek letter alpha, so alpha t squared. You see how this and this one are similar. I bet you can kind of see. And so v2, so like the W is like the velocity, right? The sigma is like your x, and then the angle is like your a, because that is acceleration, this is speed, and this is how many radians in the circle. So you probably can write out the rest of the equations, but just for grins, you've got W2 equals W1 plus sigma t, and then we can say W2 squared equals W1 squared plus 2 sigma alpha, or theta. So these are the key three equations that we're going to use when we do angular kinematics questions. So I think the best way to do this is to do an angular kinematics problem. So here's kind of a big, fat, hairy problem that we're going to attempt to solve. So we've got an electric ceiling fan rotating about a fixed axis, all right? And we know that the original is W is equal to what? 0.26 revolutions per second. Okay, notice I draw that, I don't put it slashy seconds. And we know the acceleration, or that's the alpha, is going to be equal to 0.901 revolutions per second squared. And we know the diameter, all right, D, is 0.76 meters. And I'm just going to say comma, R would be half that, and that'll be 0.38 meters. So that's the data we get from the first screen. So now we've got just the questions. First of all, is compute the fan's angular velocity. So we know the revolutions per second, so I'll say A right here. So it's going 0.26 revolutions per second. And this is where it's super good to know that one revolution is 2 pi radians, right? And I get 1.63 rads per second. All right, so that's the answer to A. For question B says, through how many revolutions has the blade turned in a time interval of 0.201 seconds from part A? So on this one, what I've got is I am going to use the kinematic equation, theta 2 equals theta 1 plus Wt times t plus 1/2 sigma t squared. Now, I know all these things, and I do believe my sigmas are in revolutions per second squared. So I'm going to have to convert this to radians per second. So 1 revolution is equal to 2 pi radians, right? So 0.901 times 2 pi gives me 5.66 radians per second squared. I can't have 1 in revolutions and 1 in radians. And the original starting radian would just be 0 plus W, 1.63, 1.63. Now we know our time. Our time was 0.201 plus 1/2 times 5.66 times 0.201 squared. And I get 0.442 radians. So that's still not the answer. How many revolutions, right? So if I know that's the number of radians, a lot of conversions, I can say that there is 2 pi radians in 1 revolution, right? And so I just take 0.442 divided by 2 divided by pi. By the way, I'm dividing by 2 and dividing by pi, or I didn't, like, you don't want to say divided by 2 times pi because that'll mess everything up. And I get 0.0703 revolutions. So it's going to go through 0.07, not very much, of a revolution in this 0.2 seconds. Question C, what's the tangential speed? Now remember, tangential speed it's v, right? I'm trying to solve for the speed, which is the velocity, but I know at the edge, and I know that the speed, the angular speed is, there we go, 1.63 radians per second. I'm going to go back out to a revolution. I'm going to say there is 2 pi radians in 1 revolution. Now it's going to give me revolutions per second, which actually I probably already knew, 0.26. This would come out to 0.26. But then I want to convert to the tangential. I can then say that 1 revolution, so a complete circle, would be equal to, remember the circumference of a circle is 2 pi r, so that'll be equal to 2 pi times the radius, and we knew the radius was right here, 0.38. Now, I don't know if you realize this, cool neat beans here, the 2 pi's actually cancel, so I'm going to take the 1.63 and times it by 0.38, and I get, not 0.63, 1.63, I get 0.62, and that's going to be, all right, question D, calculate the magnitude of the tangential acceleration at a point on the tip of the blade at a time t equals to 0.201 seconds. So now you're trying to find the tangential acceleration, and so what you've got, and actually I'm going to use the 0.9. If I on D, save myself a strep here, I can take 0.901 revolutions per second. And I can basically say that 1 revolution is equal to 2 pi as per second squared. 0.2 pi times the radius times 0.38. And that's going to give me, and I get 2.15 meters per second squared. Yeah, these are kind of long involved questions. You're going, wow, Mr. Bergmann, that's a lot. And then the last one is, question is, calculate the magnitude of the radial acceleration at the point at the tip of the fan blade. Now you might recall that this is just the centripetal acceleration, and the equation for the centripetal acceleration, A sub c, as opposed to this is like A sub t, right? This is the tangential. The centripetal acceleration is v squared over r, right? And so v is, what did we get? V was, oh, this is wrong. This is in revolutions per second, because this is in meters. This is in meters per second. So you would take 0.62 squared divided by your radius, which is 0.38, and there you go. So 0.62 squared divided by 0.38, and you get 1.01. So the centripetal acceleration is 1.01 meters per second squared, where the tangential was 2.15. Now, what does that mean, tangential? So when you're doing a circle, the tangential acceleration, as it's tangent to the circle, because the acceleration, the centripetal acceleration is always directed downward, but the tangential acceleration, as it's accelerating, because what's happening is the wheel is getting faster and faster and faster and faster, and so we're talking about it in a circle, and that's what's called the tangential acceleration. Hey, Houston, I know this can be long, and it feels like, whoa, it's a lot of stuff, and it kind of is. But it's really those simple kinematics equations that we've been using all along, and that's how you solve these problems. We don't have a problem. We'll see you in class.